This is a follow-up video from the video we did for grid connected systems using PVCircuits. In this particular video, what we are doing is that we are going to calculate manually, because we realized not so many people have access to, say, PVCircuits or PVSol. So in this case, we are going to design manually and walk through the entire process of the design. So welcome and enjoy the mathematics. So before undertaking a PV project of any kind, it is important to conduct an assessment so as to get information on the following 3 or 4 important issues. We have the shading, which will affect the PV production if there's shade falling onto the modules. We have the tilt angle and as well as the azimuth. This will dictate how much energy you get falling onto the module, so that if you are designing a new module mounting system, then you have to set the tilt angle correctly and ensure that the azimuth is also measured with a compass or mobile app so that you get the right angles. For a roof-based system though, the tilt angle is already aligned to the pitch of your roof. You realize that there's nothing much you can change about that unless you're putting up a mounting structure on top of the roof. So for the sun hours, what we need to know is that the month with the lowest global irradiation is what is critical for your design, because the other months with higher values will be taken care of, but the lowest one will affect the system if it is not calculated correctly. So we shall go through the process of determining the sun hours, the minimum sun hours, to be able to adjust our system accordingly. Then of course there's the issue of safety and security. Safety, of course, if you'll be working on top of the roof, and also you need to preserve the roof structure, so you need to take care of how you're going to work on the roof. And of course there's a personal safety. You need to protect yourself so that either there's no injuries during the installation process. Security, of course, if the items are especially for a mounted structure, then of course you must provide security for the modules, because in some areas there's a general liking for modules so that thieves easily pick them, and you are required now to provide either some protection or security fence to ensure that they're protected. If they're on top of your roof though, they are relatively hard to reach, so that's why we emphasize also this point on security. So moving further, we have 3 particular systems for PV power, and our interest is on the hybrid system, which is a combination of the off-grid and on-grid systems. In the hybrid on-grid connected system, we have 3 clear modes of operation, and we start with the day mode. And the day mode, what happens is that the PV is producing power and passing it on to the inverter, which then charges the battery. The excess power also goes into the system or into the household consumers to be used by the household consumers, and if there is excess, it passes on to the bidirectional meter and then on to the grid. The meter will record the power that you are injecting into the grid. At night, the PV system is not producing power, so what we have is the inverter being fed by the battery, and then the power goes on to supply the household consumers. Then if there's a shortfall, then it is made by the grid, bringing in more power through the bidirectional meter into the house. We can set the hybrid system to off-grid mode, and what happens in off-grid mode is the grid is not connected, so the only power comes from the PV. This is during the day, and it charges the battery, and there is interaction of back and forth just to make sure that if there's more power required by the household consumers, then the battery can meet that shortfall. Otherwise, if the household equipment are demanding for more power and the battery cannot meet that, or the battery and the charging cannot meet that power, then we shall have a blackout. So in this case, the system is just operating like an off-grid system. So before we can start our design, we need to collect data on the household consumers or the electrical components using power in the household. And in this particular case, we have the following items that are in the house that we want to consider. So there is an element of lighting, there's a security lights, there's a TV, maybe a laptop computer, there's a refrigerator and others. And here this is a wattage of each, the rating, what they're consuming, and the peak demand is of course the multiplication of the number of items times their rating wattage, which gives us the 50 hours. So we have multiplied like that and gotten this column here. So the peak demand, when all these things are switched on, is 581 watts. Then if we are now going to use this thing during the day, depending on how many hours we have allocated for each, then we find that now the daily consumption is now the multiplication of this peak demand for this particular item times the hours. Then we get this daily consumption. Then we add those daily consumptions for all the items. Then we get our total daily consumption in kilowatt hours. From here, we are going to move to the site which is going to help us get meteorological data that will help us get the lowest or the minimum sun hours, which is critical to the design. So we move to that site, and that site is this one here. So I'll open this site so that we move on to it. Then we see the process of getting the data. So when you open the link, this is what greets you. This is what you find at the site. And I need to feed in our coordinates. So I enter the figures. Let me edit. So that is the latitude. Then on this side we have the longitude. So those are our two figures. And when I click on go, it opens up the site. Then we move to the right side of the screen and click on monthly data. Then I need to select the years. So this data is starting from 2005 all the way to 2020. And when I select that, then I need to give it I'm using this one, global irradiation at an angle, because remember our pitch is going to be at an angle and the pitch angle is 22.5. So I tick on this one, then give it 22.5. Alright, then what we can do is to come here and click visualize results. So it generates this graph. What we need to do is now to download this data in PDF form. So I'll open the data. So zoom in a little bit, then we look at it. Now there's a lot of information here, but what is critical to us is this table here. And in order to extract this data, we need to use a software like Acrobat Professional, so that then we move this data to Excel. Then we can be able to process it further. So I'll do that right away. So this is our document in Acrobat Professional, and as I've said, I want to extract this part of the data, and the only thing I'll do is to export, and I want to take it to a spreadsheet. Alright, then I'll click on export. So it should process that data, and then I'll put it on the desktop, then say save. Then it should be able to open that file for our use. So this is a file extracted and brought here in Excel. So I just need to clean it a little bit and remove the unnecessary things that I don't need. So I'm left with the plain data. Let me just expand these rows a little bit. Okay, first of all, let me squeeze this one to bring it to there. Then I can just resize these rows. Maybe that's too much. Okay, somewhere there. Then I can resize our fonts a little bit, maybe say to size 10. Then pull these columns a little bit. Just want to expand those. There's a column here which is empty. There's another column here which is empty. Let me delete it. So the data runs from 2005 all the way to 2020, and those are 16 years. So what I want to do first of all is to get the total of these years. So totals. We are moving towards getting the daily average. So first of all, I'll get the totals, and this is just the sum of the years. Then it's a total average. So I'll get that, then I'll divide these things by the number of years, which is 16. So this column here should be total average. So now I copy this formula all the way down to December. Okay, then we put in the number of days. So monthly days. All right. And this is we know January is 31 days, February is 28, March is 31 days, April is 30, and so on. So our monthly days have been put. What I need now to do is to get the daily average. And basically that is this figure divided by this figure. So I'll just put an equation there so that I divide this figure, divide by this one. Then we pull this formula all the way down. Okay. So now as per this data, we see that the daily global horizontal irradiation at that angle is these figures presented here, or are these figures presented here. Now what we can see is that we have this month, which is 5.47. I'm looking at the lowest, or I'm looking for the lowest. We have 5.47, we have 5.44. I think this is the lowest month as per this data. So we will take this data and now use it for our design, noting that the lowest figure is 5.44. Alright, so I'll just copy this, then we use it for the design. From the Meteo data, the summary looks like this, so that these are the months. January, we can see that December is the lowest month, followed by the month of June. This is according to this data. Sometimes it happens that maybe around June here, maybe around June, normally this is probably the lowest month. But we can see that they're very close anyway. It's just a 0.0 something. So we are saying that it is 5.44 hours, and the reason is if you have a unit energy of 1 kilowatt falling on 1 meter square, then of course these numbers, instead of being read as kilowatt hour per meter squared, will just remain as hours. So this data has to be corrected because of inaccuracies, and we apply a 10% correction, which reduces 5.44 to 4.9 hours. So we move forward and see that for us to be able to size the PV or get the PV size out of that information, then we have our daily consumption, which we got from that table before, 530, 5380 watt hours. Then the peak sun hours now is 4.9 hours. Then we have this oversizing factor, which of course is between the AC and the DC side. So we have to make the PV larger by 1.3, and then we get, at this point, the size of the PV should be 1427 watts. So we want to use a PV, we want to use a module or a panel with this specification. This is a Jinko of 300 watts, and the other parameters are as listed. Then we determine the DC to AC ratio. So from this equation here, the power of the array divided by the power of the inverter should be between 1.2 to 1.4. Some places even from 1 to say 1.3 there, where the 1 to 1 or such, but it's normally better to oversize the PV size to be greater than the inverter by a certain factor. So in this case, we are using a factor of 1.2, and we use it to divide the size of the array, and we get the size on the inverter should be about 1189. But the on-grid inverter that is available is of size 1500 watts. So it's slightly higher, so meaning that then we should increase the size of the PV to be able to serve this inverter. So this inverter that we have selected of 1.5 kilowatt, these are the specifications. It allows a maximum PV of 2000 watts, and the rated output power is 1500, and the maximum VOC from the array should be 400. So many other parameters here which have been listed, and what we see is that it is a 48 volt charging capacity, so meaning that the batteries that it will charge have to be in series such that they're a total of 48 volts. Then those are the other parameters, and the maximum charge current is 40. So generally those are the specifications of that inverter. So if we look at the data sheet of the inverter, you will see that this is a grid tie inverter, but with very specific functions. So there is this part of self-consumption and feeding into the grid. This part is very important, and also there is the part of the charging of the battery, so that it has, you're using the power for self-consumption, but also the excess is fed into the grid. You can of course use other inverters and combine it with a charger controller, so that you have now two electronic devices there, the controller and the inverter, to give you this functionality that is on this single inverter. So that is why I've selected this inverter to be able to take us through this design. So we move forward and see that from this equation, now that because we have the inverter at 1500, we have to up the array power by using a factor of 1.2, so that it moves up now to 1.8 from 1500 that we had calculated before. So for this power, I want to use a Jinko of 300 watts of that specification, and to get the number of modules, I'll just divide the total power here by the size of the module to give me 6 pieces, and these 6 pieces I'm going to connect them in one string in series. So we check, this is an initial check, so that we are ensuring that the power of the array is less than what is stated for the inverter, and this is okay because the inverter is 2000 watts, and also the maximum point current is 9.22 because it is only one array or one string. Then it is less than the 30 input for the inverter, so this is also okay. So we move forward to do the battery sizing. The battery sizing is the system ampere hours is governed by this equation here, which is a daily consumption and days of autonomy divided by the system voltage times the depth of discharge times inverter efficiency times battery derating. Now we already know our daily consumption. The system voltage we know as per the inverter we have been given. Then days of autonomy, these are the days that the system can run without power either from the PV or from the grid. So we have set this to 1 because if you increase it, then of course you will need more batteries, and that will mean that the system will be more expensive. So we've just put that to 1. Then the depth of discharge is how much discharge, how much do you want the batteries to go down then to start recharging, and we have put that at 50% so that the system charging triggers when the batteries are at 50% discharged. The inverter efficiency we have been given is 95, and also because the battery get affected by temperature, so we'll derate the battery by 5% so that they are operating at 95%. So we put those values into that equation, and this is what we get. So the system ampere hours is 248.4, which we say is about 300. Then in order to get a whole number from here, we select this battery here at 12 volt by 150 ampere hours. So to know the number of batteries that we are going to have in series, then it is the system voltage divided by the voltage of the battery. That gives us 4 batteries which should be connected in series. And to know the number of batteries that will be in parallel, these are the strings of the 4 batteries in series, we divide the ampere hours that we have calculated divided by the battery ampere hours, and that gives us 2. So we have 2 strings of 4 by 12 volts. And this is what we are saying down here, that we have the 12 volt by 150 Ah times 4 in series, then these ones, 2 of them times 2 strings. So initially this is our layout. This is how the system looks like. We have our modules connected in series, 6 of them. Then we have our array junction box, and this is where we have the disconnect switch, we have the protection, the DC protection, then we also have the surge protection. here we have the inverter which we have selected, then of course charging the batteries, and we have a protection here and a disconnect switch. Here also we have a disconnect switch. So then on the AC side we also have an SPD, just like the DC side. Then we have a protection there. Then we have a watt meter which measures what we are producing and sending to the grid. This can be optional. Then we have the consumer unit, which of course is the place where the household components are connected. Then we have another disconnect switch to put us off from the utility side. Then we have the utility provided bidirectional meter, and this one, the way it works is that when there's excess power from our side, it works in the negative, and when there's power from the grid, it works in the positive, which measures the power coming from the grid. So in our case, we will be, when we are producing more than we need, that power is injected into the grid. We will accumulate credits which we will use against any shortfall should we need to get power from the grid. Then we have a protection here which cuts us off from the utility side. Then that dotted line separates us from the utility side. Of course, this is now the line going to the transformer by the utility provider. So our connection ends up here. Then this side is the side of the utility provider. So we need to see how to rate the components in this system, and that is our next step. So all these components, the circuit breakers, the surge protectors, the cables, we are going to rate them so that then we know how the system is fully set up. So we'll be referring to this diagram, various sections of this diagram. So maybe you need to take note because, for example, it is a cable you are doing, maybe it is this cable here, or maybe it is this DC here. So we'll be referring them by the names of the places where they are located. Then we put in the values at the final end. So starting off, we start with the cable between the solar PV and the array junction box. And this cable, the rating is governed by this equation here for the voltage. So it is VOC times the number of modules times the protection factor, which is 1.15. This should be rated at 269, but we know that the cable is rated at 1000 volts DC, so we are okay with this voltage that is running into the system, and also that the inverter maximum is 400, which is greater than what we've calculated. So that is fine for the inverter and it is fine for the cable. So looking at the current, then the current is rated at this value, so the IAC times 1.25, and this gives us 12.5 amps. So we say we use a minimum of 2.5 millimeter. And how do we get that? So we go to the table which gives the ampacity of cables to see the cables that has the capacity to carry this. Then we'll make our decision based on the information that we see. So this is table 4.1a. We shall be making reference to this table in subsequent calculations, and this table will be attached to the video page. So in our case, the first one, we have seen that we are looking at a cable that has got the capacity to conduct 12.5 amperes, and our cable will be direct, free in air. And we come to this column here and we see that there is this cable here that is 20 amps, which is more than 12.5, and this gives us 1.5 millimeter. However, this cable, we find that it is very small, and we recommend that we use the next cable, which is 2.5 millimeter. So we are going to use 2.5 millimeter square at ampacity of 27 amps. So we move back to our calculation. So we have said we use 2.5, and from the table we've seen that the capacity of that cable is 27 amps. So next we check the voltage drop on that cable. We've set our maximum to 2%, and the equation for calculating the voltage drop is given by this one here, which is the 2 times the length of the cable times the current times resistivity divided by the area, cross-sectional area of the cable. And it is required that this value, the percentage drop, should be 2%. So the information that we have the length of the cable. We are approximating 15 meters from the roof to where the inverter will be, and that is the maximum power point current, which is the 9.22. The cable is 2.5 millimeter square, which if you convert into meters square is this one. Then that is the resistivity at 20 degrees. So inserting those values, you'll get the voltage drop as 1.9, and the percentage is 32. The percentage is 0.97, and which is less than 2%, so that is okay. This is the voltage of the VMP. That is, it is here, and that is what we've inserted in that equation, times 6, which is the number of modules. So the total VMP is that one. Then we get 0.97. So we move to the next cable, which is from the array junction box to the inverter. And this is the same cable. So we don't need to do that calculation, and we don't need to do the voltage drop because the cable is very short. So we move on to the next component, which is now the cable from the inverter to the battery. So that is DC also. So from the inverter information, the maximum charge current is 40 amps. Then the carrying capacity of the cable there should be 50 amps if you use that equation. So it is the current, then we raise it by 1.25 and give it that 50 amps. So if we check from the table again, if you go to that table, you will find that this current can be carried by a cable of 10 millimeter square, which has a capacity to up to 62 amps. So that section, the inverter to battery, we are going to use a 10 millimeter square cable. Next we go to the AC side of the inverter, and we do the cable from inverter to the AC circuit breaker 1, and again we find that the current there is a maximum current there is 40 amps. So again we use the same cable as we've calculated previously. Then we check the voltage drop on that section, and it is a short cable. The current is 40 amps. The power factor has been given by the inverter is 0.99. So if you put into this equation, and please also refer to our video on the rating of cables and components. So a lot of the information is given there firsthand. So this equation here, those parameters have been explained there, so that that video should help you if you don't get what is explained here. Our figure comes out to 0.54 volts. That's a very small drop. Then the percentage is 0.24, which is less than the 2% that has been indicated there. Next, we check the inverter input cable, and we are using the maximum current that is possible from the grid. That is what the inverter will pull when it is charging. And again, if we calculate this cable, we end up with 10 millimeter square at 62 amps ampacity. So you just check in the table, find which cable has a capacity to carry 50 amps, and it will lead you to the 62, which of course you will see that it is a 10 millimeter square cable. Next, we look at the fuses and SPD. So we start with the fuses. So for the fuse, this is a condition as provided by IEC 62738, that the fuse rating or the trip current should be ISC current times 1.25, and the ISC current is 10.02, and if I multiply that, I get 12.5. So the fuse, remember the cable, we have done it at 2.5 millimeter, and it has a rating of 27. So the cable is safe. We are not worried about the cable. So we are worried about the protecting the panels. And we know that the reverse current rating of the panel is 15 amps from the specifications that we saw earlier. So, and that is a condition here. So when we calculate, we find that the rating of the fuse or MCB should be less than or equal to the reverse current rating of the module, and our fuse that we select from this condition is a 13 amp 2-pole and at 1000 volts. So next we do the rating of the DCCB rating. This is the one protecting the connection between the inverter and the battery. And we know that the current passing along that route, the maximum current is that, and the cable ampacity therefore should be 62 amps. So for the fuse, we have selected the fuse which is going to be at 50 amps, 2-pole and 1000 volts. And because it is a cable you are protecting here, and the cable already has a capacity of 62 amps. So we are safe. We have protected that cable. Next, we look at the SPD, and SPD are selected as per the information provided by the manufacturer, and the system, our system operating voltage is about 270 volts VDC. So this is the nearest that can protect that line, and it has a maximum continuous operating voltage of 350. On this side we have the AC. Our AC is operating at 230, so this is the closest to it at 277, and with a maximum continuous voltage of 350. This information is provided by the manufacturer of the SPD, and they have reference guides on how to select the SPD. So for example, here we have selected the LSP type for the DC side and a little fuse for the AC side, but you can select according to what you have in your region or as per your specifications. So this is our line diagram capturing the information from the calculations that we have done. So we can see that we have put in the protection there, the first DC CB rated at 13 amps. Then we've put the protection for the battery, which is at 50 amps. Then going to the cable coming from the inverter. This cable draws a current, maximum current of 40 amps. So we've put it at 10 millimeter square and provided a protection of 50 amps just in case it exceeds the cable rating. The cable rating ampacity is 62 amps. Then it is the same cable running through to the utility side, and the first point of protection is the same as this other protection here, just to ensure that we have maximum protection for our inverter. Then that is the utility side, and this is a utility side transformer where our power, once there is excess produced from our solar system, then it can be injected to the grid by our inverter. That is the final line diagram. So let's proceed with the final part of the design. So in this section we look at the materials that have been used in the design, and this is just a rough guide on some of the key items that are involved in the system. So we start with the PV modules. We can see here that is our Jinko Solar 300 watts, and there are 6 of them, totaling to 600. Our inverter Infinisolar, which is at 1.5 kilowatts, I've estimated the price to about 400. Then the batteries, this one takes a major share of the cost because there are 8 batteries. Each I've estimated at $100. So some of this cost, some are generic, some are close to real world prices. You can adjust according to your region. So other components like accessories and wiring and some other items like surge arresters, all have been included. So some minor studies and of course engineering, some of the monies that you are likely to incur, including environmental studies. Then we come to the installation. So this is a global installation cost because we just have one inverter. So I've estimated that to about $150. Then maybe some money for connection to the grid. Of course you will incur some cost there. Something to cover for transport. Then totally the amount is about $29.40 USD. And looking at these assets, the one which are depreciable comes to about $27.40. Then we don't forget the major operation cost. We will need to be cleaning the modules because there will be the element of soiling, so they'll require maybe after some period they are cleaned to remove dust and particles which have settled on the surface. This is per year, these costs are per year. The other ones are per item. So we see that the amount, minimum amount I've put there for the maintenance per year is about $290. So, well, depending on your case, this may be lower, this may be higher. So there we are. So on the summary here, we see that the total installation cost is $29.40, which we saw above here. Then the operating cost, of course, that is $290, which we saw here. Then the unused energy, this is energy that we are using ourselves by the household consumers. This is 1964 kilowatt per year. Then this is the energy that goes to the grid as per the system. Then the cost of produced energy. This is a bit lower, 0.155, but of course, depending on how you've configured the system, then we are roughly there. Some places this figure could be, say, about 2.2 or 0.22, something like that. So, but remember that the system is to help us save on high bills, and it works in the sense that if we have excess energy, then we have credits in favor of the system, and when we are drawing power from the grid, then the savings that we have done on the credits will be used against to offset those expensive power from the grid. So that is the system. So once again, thanks for your time. We thank you for having followed the presentation up to this point. So keep it here for more videos like this. Bye bye for now.